without any further ado, I am going to introduce our next speaker. So Michela Massimi is a professor of philosophy of science in the Department of Philosophy at the University of Edinburgh. She's affiliated with the Higgs Center for Theoretical Physics. For those of you who do not know, Peter Higgs is who of course has the name of the particle, is a professor at Edinburgh as well. He's been there for a very, very long time. And she's also a fellow of the Royal Society of Edinburgh. She did her PhD at the London School of Economics and taught at the University of Pittsburgh, University of Florence, and the University College London before moving to Edinburgh. Her primary research interests are in philosophy of science, the history and philosophy of modern physics, and Kant's philosophy of nature. And among many honors, she is the recipient of the Royal Society's Wilkins Burnell Medal and lecture, which she gave in 2017 in May when I was there as well in London. Okay, so let's welcome Michela. Thank you, Michela.
Thank you very much, Marcelo. Thank you. Thank you very much, Marcelo, for having me and Mark for this month.
I forgot to mention, that's
right.
No,
exactly.
Michela
so we are
is a fellow
at
of
the
our
Institute
institute,
for
yes.
Cross-Disciplinary Engagement, and it's been three really stimulating, wonderful 3 weeks. So thank you so much for having us. Thank you for organizing this conference. Can you hear me okay? Is the microphone okay at the back? Okay. So thank you all for coming, bright and early, 9 o'clock. I said to Marcel, I'm not an early morning person, so you'll have to bear with me. It'll take me a few cups of coffee to kind of warm up. Just to give you a little bit of background about this conference and where it all began, really. It all began because earlier this year, I think in January, we got the blind spot on Aeon, and just a few weeks later, I myself published an article called Getting It Right. So when Marcelo was planning my visit here, the idea was to organize a conference that would bring together a group of people, physicists, philosophers, cognitive neuroscientists, with common shared interest on questions about epistemic agents, objectivity, and truth in science. So you might have seen from the subtitle of this workshop that it mentioned the search for truth. Truth has appeared in some form yesterday in various slides. There was primarily a discussion about objectivity and mind dependence and subjective Bayesianism and the epistemic agent. So I want to deliver on the notion of truth in my talk today. And I want to start with some pretty mundane observations. Why truth matters, why we should care about truth. And I think those are three familiar examples and headlines that I think should make us all as philosophers pause and reflect about why truth matters in science. Truth matters because we want to know and find out exactly the effect of, for example, climate change on agriculture and on how our environment is going to be affected in 20, 30 years down the line if we continue with carbon monoxide emissions. Truth matters because we should all be concerned about what the UN has reported as a surge in cases of measles worldwide in 2019 because of an anti-vaccine trend that has spread through social media. And truth matters whenever we consider the economic forecast, where we want to make predictions about what will happen in some economic scenarios, right? What happens if we're in or without the EU, for example, if you come from a country like myself in the United Kingdom. So those are really mundane examples that shows how discussions of truth really affect us all on a daily basis. Now, what is interesting is that as philosophers, we have come a very, very, very long way from truth. In the past 20, 30 years, there's been a long disenchantment with the notion of truth in science. And I gave some of the reasons in the article in Aeon that, I mean, if you want, you can go and read. And I ended up ruffling a few feathers of social constructivists in publishing that paper without really knowing that I was going to somehow do that. So I want to mention just 3 strands of this disenchantment with truth in philosophy of science. It's not meant to be any exhaustive overview of why we got disenchanted with the notion of truth. So just 3 examples that I think have been salient also for my work and my research. The first has been an attention paid to scientific modeling in science and the acknowledgement that in any given context, in any given domain of inquiry, there might be a plurality of scientific models. So classic examples that you find in the literature I'm working on comes from nuclear physics. If you want to know what is a nucleus, tell me the truth about the nucleus, right? You turn to physics, you turn to nuclear physics, and it seems that physics tells you, okay, there are all these different models about the nucleus. Each of them can be used in a different context. So there are 4 main families of models. There's a liquid drop model, the one that you have there at the very bottom, that we use if we want to study the role of the nucleus in nuclear fission, for example. But then you have the shell model, which is this one here on the right corner. And that's useful if we want to study chemical reactions and radioactivity, for example. It tells us that a nucleus is a set of protons and neutrons. They are distributed in shells. They are concentric shells according to rules that follow the Pauli principle. But if we're working on obviously particle physics, the model that we would use is the quark model up here that tells us, well, think of the nucleus really as constituted of protons and neutrons, composed of 3 main valence quarks swimming in a sea of quark and anti-quark and gluinos exchanging quantum chromodynamical forces. If you're interested in Big Bang nucleosynthesis, you will turn to the cluster model that tells you that nucleus is like a tetrahedron structure where protons and neutrons are clustered around the corner of this tetrahedron. Now, a physicist may say, okay, what's the problem with that? Philosophers have been thinking about what kind of philosophical lessons we can draw about realism and anti-realism in science from very common situations exemplified by this example, okay? And one of the lessons that have emerged loud and clear is that maybe we should think of models just really as tools to get things done. That's what physicists do in different contexts, depending on what you want to do, whether you want to explain Big Bang nucleosynthesis, or you want to explain nuclear fission, or you're interested in understanding quantum chromodynamical forces, you resort to different models. So you have a pretty nonchalant approach in how you use those models. But don't take those models as literal descriptions, obviously, of anything that exists in nature. I mean, this is correct, because obviously models are idealized, abstract representation of the target system. But in a way, it's also invited considerations about why truth is not really what we are after in science, because it seems, looking at modeling in science, that what we are after is something slightly different. We're after a series of representations that may turn out to be useful in different contexts for different purposes. Another example of why there has been this disenchantment with truth in philosophy of science over the past 30 years or so, and obviously goes back to Thomas Kuhn, absolutely towering figure in the history and philosophy of science, which is really primarily my field. From the 1960s, from the year of publication of The Structure of Scientific Revolution, Kuhn put forward a very radical new image of what science is all about. So in his view, science does not aim at truth. Truth is not the aim of the inquiry. You got that quote where he says, does it really help to imagine that there is some one full objective true account of nature, and that the proper measure of scientific achievement is the extent to which it brings us closer to the ultimate goal? And his answer is no. And he gives this beautiful example, actually, in his very first book, which is The History of the Copernican Revolution. That's how he started. He started teaching the history of physics when he was, I think, at Harvard. And that's how he got into the history and philosophy of science. He records in his autobiographical notes that he had to basically teach himself Aristotle physics and trying to make sense of what physicists of the past were trying to do. And so he gives this beautiful example about the shift from Ptolemaic astronomy to Copernican astronomy. You might be familiar with this, but why did we embrace Copernican astronomy? Well, if you read Kuhn, the answer is not so much because Copernican astronomy is more likely to be true than Ptolemaic astronomy. In a way, Ptolemaic astronomy worked pretty well for a long, long time. The reason, the motivation for shifting from Ptolemaic astronomy to Copernican astronomy, in his view, was the fact that the church at the time was looking for a new calendar to establish the date of the Easter. Do you know this story? Maybe it's familiar. Do you know why the date of the Easter changes every year? Yes, someone knows. How many of you don't know why the date of the Easter changes every year? Okay. I discovered this by reading Kuhn. So why is it that Christmas is over 25th of December, where Easter sometimes is beginning of April, end of April? Because in the Christian calendar, the date of the Easter is determined by the first Sunday after the full moon, after the spring equinox, okay? So you use the spring equinox, you get the first full moon after, the Sunday after is the date of Easter. Now, because the lunar months are not exactly the same every year, the date of the Easter changes with the date of the lunar cycle. So determining the lunar cycle was very, very important, and what you have here are the Alphonsine table that were used at the time of Ptolemy to determine the full moon month by month. But there were problems with the Alphonsine table, and one of the big motivation for the shift from Ptolemaic astronomy to Copernican astronomy was precisely the church need for a new set of astronomic table, what became eventually the Protenic table, and later on with Kepler, the Rudolphine table. So you read Kuhn's account, and you clearly get the impression that truth doesn't really matter, because what matters is that we have very specific problems, and science is determined by puzzle solving and increased puzzle solving, not by the search for truth. There's a third reason why there has been a disenchantment with truth. And this is a reason more, again, internal to the history of science, but had a huge impact on philosophers of science reflecting on science. Truth and success don't necessarily go hand in hand, and it's something that philosophers of science have made loud and clear from the 1980s. So there's a famous article by Larry Lauder on this. It's not the case that successful scientific theories are necessarily true theories. It's not necessarily the case that success is the track record for truth. We have plenty of examples from the history of science of theories that were once very successful, enjoyed a good degree of success, but turned out to be false. And so the repertoire goes from the geocentric system to Maxwell-Honeycomb model of the ether in 1861, to Dalton. So this is Dalton, one of the fathers of chemical atomism, still portraying atoms with little spikes of caloric. So he believed that there was this imponderable fluid called caloric that was responsible for thermal phenomena. And he believed that atoms came surrounded by a little shell, little spikes of caloric. So if you are in that kind of exercise of looking at the history of science and looking at an example of successful theory that turned out to be false, again, it seems that we get a pretty kind of negative scenarios about the role of truth in science. Now, what I want to do really today is to defend the truth in science, and I think why it really matters, and I gave you the first slides, just really to remind ourselves as concerned citizens about why truth matters in science and why we should realign some of our philosophical discussions on those issues that really matters for our society. So I'm gonna start with a question: does it even make any sense to talk about truth in science today? I mean, given all this development in the history and philosophy of science of the past 20, 30 years, all these really detailed studies that have been done by distinguished historians of science and philosophers of science. And my answer is yes, it makes sense to talk about truth in science. We need to understand what we mean by truth in science. And it's worth distinguishing between truth on one end and views that have appeared yesterday already in various talks, and I'm just going to cluster under a very generic umbrella of a Thomas Nagel view from nowhere, okay? I think one of the problems in this literature is that very often attacks against truth have gone hand in hand with a attack to an Hegelian view from nowhere, to the presumption that there is one single monist objective description of the world, which clearly flies in the face of pluralism that we observe everywhere in science, okay? But on the other hand, you want to distinguish also truth from big varieties of families that goes under the name of relativism and constructivism, and have also been very popular in the science and technology studies literature, in the sociology of scientific knowledge, and so forth. So where to go from here? Where? Okay, this is where I want to go. I'm not sure you want to go in the same direction, but this is where I've been going. I think we need to think of new ways in which science is in the business of telling us truth, a way that really takes on board seriously the lesson coming from the history of science, from science practice, from modeling, that our knowledge is situated, is historically and culturally situated, is pluralistic. It comes in a plurality of theories and models. There isn't one single an Hegelian view from nowhere, but that doesn't mean that there is no truth, okay? So a possible way of thinking about this, I'm not saying it's the only one, I'm not saying necessarily it's the best one, I'm not here to sell perspectival realism as a view, but it's the view that I've been trying to explore over the past few years. It's a view that really begins with a 2006 book by Ron Geary called Scientific Perspectivism. And in a way, it's a view that has a much longer philosophical pedigree, because it really goes back to intuitions by Kant, by the American pragmatist, by Hilary Putnam, by lots of people that throughout the history of philosophy have made this point about how science is part of our cultural history, but nevertheless, science has something to tell us about nature, so we shouldn't necessarily abandon the quest for truth. It's just a matter of how we rethink the topic. So this is Ron Hone take. It says, I want to defend a kind of realism, but a kind of realism that I'm going to call perspectival realism, which I think better characterizes realism in science. For a perspectival realist, the strongest claim a scientist can make are, according to this highly confirmed theory or reliable instrument, the world seems to be roughly such and such. Now, this is, as I said, is the starting point of a journey that I've been doing over the past few years, because there are some dots that need to be filled in Ron's picture. So there is, in a way, a metaphysical tenet that says facts about the world are perspective independent. That's why it's a kind of realism, okay? We want to defend the view that we don't make the world, we don't construct fact. Okay, there are facts about nature that exist mind independently, a perspective independently. But then in an obvious way, our scientific knowledge claims about these facts are perspective dependent. Our knowledge is perspectival, depends on us as epistemic community at any given historical time. The missing link, I think, between those two really is a notion of perspectival truth. And so what I want to do in the rest of this paper is to very briefly shine a spotlight on the realist and perspectival component. Section 2, present what I take to be a minimal realist commitment and the argument from success. And in section 3, really sketch very broadly a notion of truth across scientific perspectives. How am I doing with time? Because I kind of, we started a bit late, but. Keep going, okay, keep going. When you, give me a sign when, okay. Okay, great, okay. So let me get clear about the realist and the perspectivalist component. What is it like to be true within a scientific perspective, and why does this question matter in a way for science, okay? Now consider, again, for those of you that heard me talking about 10 days ago here, I gave a talk on the history of the electron, which I'm not going to repeat today, but in that talk I was looking at how our realist commitment to the electron, in particular to the electric charge, emerged at the end of the 19th century, beginning of the 20th century, as a result of different perspectival journeys, different characters, different authors in this narrative. So obviously there is J.J. Thomson on the left-hand side, whose cathode rays experiment is regarded as a defining moment for the discovery of the electron, but he didn't even call it electron, he called it a corpuscle, and he had a view that was still very much entrenched in what might be called the Faraday-Maxwell electromagnetic view. So he believed that his corpuscle was the end of a Faraday tube with positive and negative electric charges that you could stretch and bend and break. And he was working within a tradition that was trying to explain electromagnetic phenomena, really from the time of Maxwell honeycomb model of the ether that I've shown earlier. More or less at the same time, well, a few years later, you find Max Planck in his second edition to the theory of heat, announcing that his theory of quanta is the best theory in town because it's the one that provides a value for the electric charge, which is closer to the experimental value found by Perrin and others. And he had a completely different, if you like, perspectival representation of that object. So he believed that there were actually electric charges at minimal quanta of electricity, and he believed that the quantization of electricity along the line of the quantization of black body radiation was the best example of how nature is quantized. Matter and radiation and electricity are all quantized. I'm not going to repeat the story because, as I said, I gave a talk here just 8 days ago, and I'm sure, I think it was filmed so you can catch up with a little of the story. But this is an example where you see how realism and perspectivism go hand in hand. We're interested in finding out the nature of reality, the nature of electrons and electric charge. At the same time, we are immersed in our scientific perspective, whatever those are, right? Thomson was working really within a well-defined tradition about electromagnetic field, as much as Planck was launching his new research tradition about quantum theory. And then there's the third element, which is the history of electrochemistry with Helmholtz, but I'm not going to tell you about that. So in a way, there is this epistemic pluralism that is widespread, and it doesn't just affect models of the nucleus, it's everywhere in the history of science. Our beliefs about which theory is true do change over time and across scientific perspective. You may say, is the electron that we now believe and embrace today the same electron that J.J. Thomson actually didn't even call it electron? Is it the same things that Planck believed in? What about the concept of the electric charge or the concept of spin? How have they changed remarkably from, say, the time of the old quantum theory to contemporary quantum electrodynamics? Perspectival consideration of this kind that really seems to shake, in a way, the realist tenet about believing the theory to be true. Because the question is, how can anyone ever be in the position of claiming to know that her belief that theory X is true is indeed correct? So one of the problems that I think we are dealing with when we think about truth in science and we think about the perspectival nature of our knowledge is that there seems to be some mismatch between metaphysics and epistemology, and we want to realign metaphysics with epistemology in a way. We don't want metaphysics kind of to run free on their own on the basis of some Hegelian view from nowhere. At the same time, we don't want to fall into the opposite temptation of saying, well, there isn't really a perspective-independent way the world is. It's all a matter of being within perspective, or as Kuhn would say, within scientific paradigms. There is no overarching truth as the aim of inquiry. But the tension is there, and I think it's a tension that we're all aware of and that we're trying to address in different ways, in different forms. So this is a possible way of addressing that tension. I'm going to call it a minimal realist commitment. I think there is a minimal realist commitment that we can all, hopefully, agree on. And it's minimal because it doesn't buy into any overinflated, overblown metaphysical picture about what there is. And it doesn't buy or fall into an Hegelian view from nowhere. So it's kosher to the realist program of getting things right. At the same time, it is meant to be sensitive to consideration coming from the scientific practice, pluralism, and the history of science. I think getting things right is at the heart of the realist program. If one wants to call oneself a realist, this is the minimal realist commitment one should take. Imagine an instrumentalist or a constructivist or a relativist. Any anti-realist of any kind wouldn't share the same normative commitment. You can't really imagine, I don't know, a relativist saying that science ought to make facts relative, or a constructivist saying that it's the a goal of science so no, it's the science ought to construct fact. This element of normativity is something that is really distinctive of the realist intuition. At the same time, we need to be careful because the way I understand this notion of getting things right is not in the standard ways in which scientific realists think about getting things right. We shouldn't think of truth as sometimes I see referred to as the capital truth. I never understood this thing about the capital truth. But anyway, kind of fall into that stereotype of whatever capital truth with the capital T means. We shouldn't think that there is a theory necessarily of everything that is waiting at the end of the inquiry as the final aim, the final goal, as the final moment where we unveil the veil of Maya and we discover, ta-da, here it is. Because it's really not what science should aspire to, assuming one as realist leaning. Instead, it's what science ought to do by realist life. So I see this normative commitment, okay, that I think it's a commitment that we all should take if we really care about science and if we care about science in society. If we care about the issue that I mentioned at the beginning of those talks, then that's where you can see why truth and realism matters, okay? Science ought to map onto reality in a truthful way. So to judge a scientific theory or a model to be true is to judge it as one that demands or commands our assent, something that we can agree on, okay? Something that we can't help but agreeing on. So in the end, I want to suggest that really getting things right is a norm about what we take science to be about. Really mapping onto nature in a truthful way. And probably mapping here is not the right word, okay? It's just for lack of a better word. In the simple-minded sense of making our scientific claim correspond to perspective-independent states of affairs that can adjudicate their truth or falsity. So I'm a realist. I totally agree with the realist on this, and I think it's perfectly fine to go along the lines of the realist in saying that this is what science is about. And there is nothing incompatible with defending the view about truth while also being sensitive to the history and the practice of science. You can scratch your head at this point and say, wait a minute, isn't this just standard scientific realism? How does that differ from the classic story that we have heard all along about there is a mind-independent world, the aim of science is to tell us theories that's the best of our knowledge within fallibilism and obviously mistakes that are always possible, we believe to be true. How can we actually defend a view if we really take seriously the challenge coming from Kuhn or from epistemic pluralism? How can anyone ever know that she or he is indeed getting things right if we take the Kuhnian narrative about science seriously, that we are immersed in our scientific practices, immersed in our scientific paradigm or scientific perspective that we want to call it? Now, the classic response here from the realist tradition has appealed to the notion of success. So scientific realists would defend the view that scientific claims are true or get things right to the extent that they are either explanatorily or predictively successful or both. So surely there were theories that were successful and turned out to be false, like caloric, ether, and many others that I mentioned before. But a realist would suggest that we have to look at the predictive success, the novel success of theory as a guide for truth. How do we know that we're getting things right? We just look at the performance of the theory. But obviously the perspectivalists come back, and you can see this tension all along, okay, this sort of dialectic between the realist and the perspectivalist component, whose success and by whose light. And here there are two pluralist takes on success that I'm just going to mention, and I'm going to give you very briefly the reasons why I think we should not go down those lines. So here's a possible way of solving the tension between the realist that says, of course, just look at the track record of science, look at success, and that will be the guide to getting things right. Perspectivalist, Kuhnian, historical consideration comes in and say, no, wait a minute. You can't do that because how do you assess success? So how do you reconcile the tension? Possible strategy, success from everywhere. So you can be a thoroughgoingly pluralist about science and assume that success is the guide to getting things right, but not a sort of one unidirectional notion of success. So we can use standards of success of different scientific paradigms, different scientific perspectives at their own time as the criteria of success. Now, much as I want to think of myself as a pluralism, and I think this is an important point that the pluralist has, a notion of success from everywhere is really not going to do any job for us, because it's not going to really be able to tell us the difference between Ptolemy and Copernicus, okay, or between the phlogiston theory and the oxygen theory. It's going to deliver an impoverished picture of how is it that we're getting things right across scientific perspective. So I don't think that that option would do, although you find defenders of that view in contemporary philosophy of science. Then there's another possible option here. You can say, well, let's be pluralist about science, about the history of science, but let's just assume that we judge success by our own standard now. After all, we are the one looking back at the past and establishing whether we got things right or not, right? So from our point of view now, we now know that Copernicus got it right and Ptolemy didn't, and we now know that Lavoisier got it right and the phlogiston of Stahl got it wrong, and so forth. It's a classic move that you find again and again in the philosophy of science literature, but I have my worries about this, and I wrote a paper a few years ago on this that you can find on my website. It's called Bringing Realism Back Home. I have my worry, and the worry is that a view of success from here now is nothing but a disguised Hegelian view from nowhere. It's just that we take our current standpoint as the Hegelian view from nowhere, and we just can't do that, because our current standpoint, our current perspective is one among many, many others that preceded us and that will follow us. It'll come and go, as any other theories have come and go, as any other scientific perspective have come and go. And more than anything, really, I think this view from here now is going to end up into some sort of tension, okay, where there's a tension where states of affairs that were deemed to be true here and now become false there and then. Imagine a scientist in the Middle Ages working within the impetus theory, right? I mean, from their point of view, Aristotle's physics was getting things right up to a certain point. But from our point of view now, Aristotle's theory doesn't get things right anymore. So you can't have this notion of from here now, because the here now moves. It's just like what Jenan was saying yesterday in a way, and we move along that line. So we just have to recognize that we not only we are not in a better position than people in the past, but we are going to end up with a contradictory view of what counts as true or false, precisely because of our standpoint moves along the history of science. So where to go from here? Okay, truth across scientific perspective. This is my third and last part of this talk. Okay, I want to suggest the notion of success from within, not from everywhere, not from an Hegelian view, not from here now, but from within the history of science. I think if we engage with the history of science, if we engage with the detail, the beautiful nuances of our scientific history, we actually have a positive, optimistic story to tell about how we got as far as we have got. I don't think it's a negative story. I don't think it's a story of pessimism. I think it's an optimistic stories of success from within well-established scientific traditions. We do that all the time. We don't have a God's eye view. We don't have a privileged standpoint. We can't pretend that our current standpoint is a privileged one. But nevertheless, we are in constant dialogues with our predecessors and our rival in contemporary history. And it's that dialogue that produces success from within. So let me give you an example, okay? And this is really a toy example that you find discussed in the literature on perspectivism. Suppose you're interested not in the nucleus, but in water, okay? Something as simple as mundane as water. You want to find out, tell me about water. Tell me what is the metaphysics of water, what are the fundamental properties of water. Tell me the truth about water. And you may end up with a statement as simple as that. The water is a fluid with viscosity. Now, there is a sense in which the truth conditions of a scientific claim like that are sensitive to the perspectival context of use. If you're working within fluid dynamics, that sort of sentence is true. But if you're working within statistical mechanics that treats water as a statistical ensemble of molecule, well, strictly speaking, that claim is false, right? Water is not technically a fluid. That's a macroscopic property. The reality is that water is a bunch of statistical ensemble of molecules. So examples like this, you'll find them in the literature as arguments for saying that different contexts, different perspectives, in the sense of modeling practices and so forth, may tell you different things about the same target system, and what might be true in one perspective might be false in another. But I think it would be really a big, big mistake, a mistake not to be made, to think that what goes on in those situations is some sort of making truth relative to perspective. There is no truth relativism here. It's a very simple, well-known, well-studied semantical fact that conditions for truth are sensitive to the context of use. So we should go contextualist about those sort of examples. And sorry, this is the paper on which I'm drawing what I'm following. So in that paper, I distinguish between different ways of thinking about perspective dependence, the relativist, the contextualist, the indexical view, and so forth. And ultimately, I defended the view that I call the four kind of perspectival truth, whereby knowledge claims in science are perspective dependent, where the truth conditions, understood as rules for determining truth values based on feature of the context of use, depend on the scientific perspective in which such claims are made. Yet, such knowledge claims must also be accessible from the point of view of other subsequent or rival scientific perspective. And it's really the last part that carries the realist weight, okay? So, of course, truth conditions are contextual. We have heard this again and again. We have taken on board the lesson. Does it mean that truth is relativized? No. Does it mean that there is no way of getting things right? No, we do, and we do it all the time. In fact, in the case of water, okay, sorry, this is okay. I'm gonna skip, no. What was it, the case of water? I think I'm, sorry. I might have skipped some, okay. So in the case of water, we know how to do that because we know exactly how to translate the language of fluid dynamics into the language of statistical mechanics. And any physicist that work in the area will be able to tell you how you can effectively retrieve viscosity as a property of water as a derivative property from some of the fundamental properties in statistical mechanics. So the idea is that you can imagine an assessor that will be able to conclude that there is no loss in the truth evaluable content of the sentence during the perspectival shift from hydrodynamics to statistical mechanics. So despite the perspective sensitivity expressed by perspectival truth, we can still be optimistic about our partial, idealized, incompatible model getting the properties of water right. Now, obviously, we need to be careful here because contextual truth conditions are understood in different ways in different kind of quarters in philosophy of science. So the way I've been thinking about contextual truth conditions when it comes to philosophy of science and debates about scientific modeling is along the lines of what I call standards of performance adequacy. Namely, we want to look at how well our knowledge claims travel across time, across scientific perspectives, whether they still serve us well, whether they serve well the epistemic needs of different communities. And those are just some standards that we use across scientific perspective. It doesn't matter if you are Ptolemy or if you are Copernicus, if you are Lavoisier or if you are Stoll, or Priestley or whoever else. There are some standards that stays the same. And for example, accuracy with respect to fundamental mathematical equations, empirical testability, projectability, the ability to feature in laws of nature, the heuristic fruitfulness across a variety of engineering and other practices. Those are standards that we share, typically we do share, no matter how different and sometimes radically different the images and the representation of reality might be across different perspectives. So yeah, this is the slides I was looking for. So it is indeed possible to assess the performance adequacy of knowledge claims in hydrodynamics from the point of view of non-equilibrium statistical mechanics, when you can retrieve a viscosity from the macroscopic dynamics using various approaches. Now you may think, okay, this is a toy example about the water, okay? No one really doubts about water or the viscosity of water and so forth. And probably we have a well-defined, well-understood mechanisms for translating, if you like, the language of fluid dynamics into the language of statistical mechanics. So the tension between the realism and the perspectivist component get easily resolved. But what about historical perspectives, okay, where things get a little bit more tricky, okay? So what about situations where, we used to believe that the electron was a structural element of an elastic ether. So Joseph Larmor, Lawrence, as I said, in some way, Thomson, Corpuscle, we no longer believe that. But we used to believe, at least since 1924, with Pauli, that the electron has a integral spin. Kronig came along, gave this semi-classical model with the spinning top. We no longer believe that, but we still believe in the spin, right? So what makes us believe that C is still true, despite perspectival changes about how we think about the electron spin and always a spinning top, while we no longer believe B to be true? What can be said about that? Well, I don't have any kind of smoking gun answer here, okay, to that question. I think it's an important question, a very, very difficult one. But okay, let me hint at a possible answer to that question. I believe that we no longer believe in the first sentence to be true, because now we believe that that claim that the electron is a structural element of an ether has really failed to satisfy the very standards of performance adequacy it was meant to satisfy. So how do we know that we're getting things right? Let me go back to my question. How do we realign metaphysics and epistemology here, okay? I think Kuhn had a point when he said the end of a paradigm is because the paradigm implodes by its very own standards. It reaches a point where there's an accumulation of anomaly, it just doesn't work. It wouldn't work until you replace it. So in a way, the standards of performance adequacy tell you that you reach a point where you end up with a theory like the phlogiston theory that, for example, is inconsistent, tells you inconsistent stuff, okay? And that's why at some point we abandon some of the knowledge claim that we used to hold dear. By contrast, the claim that we still hold on about the electron spin, again, we believe it to be true to the best of our knowledge because it continues to perform well, it continues to perform adequately with respect to standards of performance adequacy that it was meant to satisfy. And obviously here there is no algorithm, there is no recipe, okay? So if you ask me, okay, how am I going to assess this? It's through the history of science. It has to be case by case. The mechanism for cross-perspectival assessment may vary. So sometimes you have a knowledge claim in a given perspective that becomes a limiting case of a more general claim in a new perspective. I guess that's the case for, say, the Bohr correspondence principle, classical examples, how you try to retrieve some of the laws of classical physics in the limits of high quantum numbers. In some other cases, like the example of statistical mechanics and fluid dynamics, we have fairly well understood interreduction rules. So there is no general algorithm or recipe, but that doesn't mean that we don't have standards for cross-perspectival assessment. We do have those standards, and that's what does the realist job in the end. I'm going to conclude just by mentioning some challenging scenario for testing perspectival realism that I'm not going to discuss it, really, just going to give you the picture there. Things that have been working as part of my project. What happens when we are in uncharted territories? What happens if we are working within a well-defined scientific perspective, say the standard model, and we are trying to find out whether there is a new physics beyond the standard model, okay? That's a really interesting question for perspectival realism. How do we make that jump? How do we use the resources that we currently have, our current models and technique and instruments to possibly shift to a different scientific perspective? How do we know that we're getting things right? So I've been doing some field work with colleagues at CERN about the CMS experiment and the Atlas, looking at specific modeling techniques that they use in the context. I'm not going to tell you that story, you find it on my website. Another interesting testing case is a case of cosmology, obviously. Another example where we are really in uncharted territories. So we believe, to the best of our scientific theories, that there should be dark matter and dark energies in the universe. But how do we go about looking for those objects? So I've been working with colleagues at the Dark Energy Survey, attending some of their collaboration meetings, and I got really intrigued by, this goes back to Chris' example of the Bayesianism yesterday, the use of priors to pack knowledge that then we can use to make assessment about evidence for dark energy. So if you read the dark energy result that just came out last year, it's a fascinating story about how much knowledge we need to presuppose in those prior. That's a table of prior, main cosmological parameter, nuisance parameters, who sets those prior, how wide ranges should those priors be, why do we pack some of the assumptions about, well, lots of other stuff really in the matter density and neutrino density and so forth. Final example from dark energy to dark matter, even a better example of the perspectival nature of our knowledge. What happens if we have to simulate the formation of galaxies using computer simulations? And what kind of role epistemic agents and assumptions about baryonic feedback, for example, play in retrieving well-known astrophysical data, such as the relation between the baryonic mass and the acceleration in galaxies, the so-called baryonic Tully-Fisher relation. As I said, those are just a snapshot. You can find details of these 3 different strands of the project that have really been looking at some of the cutting-edge work in particle physics and cosmology on the website. To conclude, is perspectival truth true enough? I think the metaphysical quest for tracking perspective-independent states of affairs is ultimately complemented here by an epistemic stance about us as epistemic agent and our ability to assess the continuing performance of other agents' knowledge claim by their own original lights. Is this true enough? I think it's the best bet that probably we have about being realist, while also taking into account the perspectival nature of our knowledge. And I conclude here. This is the website where you find information about the project, the activity, some of the publication that I simply mentioned. Thank you so much.